In this video I'm going to do an example using my result that I've got for vector projections or vector resolutes. So here's my example: resolve vector A into components parallel to and perpendicular to vector B, where A is negative 3i plus j and B is negative 2i minus 2j. We don't need a diagram to do this, but often when we're learning a concept it's helpful to have something to visualize. So let's try and draw vector A and vector B, a sort of rough sketch, and then understand what it is that we're actually working out. So negative 3i plus j, well, let's say that's negative 3i plus j, and then negative 2i minus 2j would be something like that. Alright, so we're trying to get A as the vector sum of a component parallel to B and perpendicular to B. So grabbing another color here, I could say there's a component of A in the direction of B plus a component perpendicular to B, and so I could call that, just for ease of use, I could call that a vector u plus a vector w. So resolving a vector into components is the same as finding the vector projection of A on B and then the vector projection of A perpendicular to B, or finding u and w. So I'll use the first version I produced, which isn't the one that's on your formula sheet, and then I'll just sort of try and show you that we can do it with the one on the formula sheet as well. So I said that we could calculate the u, the vector projection of A on B, by taking the dot product of A and B, dividing by the dot product of B with itself, and then saying that's just multiplied by vector B. So that's that's the amount by which I'm scaling up or down vector B to get vector u. So subbing in here, and the reason this definition is easy to use is that we're just finding dot products. So A dot B over B dot B times vector B. So that's equal to, what's that? Negative 3 times negative 2 is positive 6 minus 2, so that's going to be 4. And then we get 4 plus 4 is 8. Negative 2i minus 2j, putting that back into component form. So basically it's a half times that, isn't it? 4 over 8 is a half, so a half times that. Well, I picked some numbers here that work out really nicely. Often these won't work out like this at all. They'll be sort of fractional or you know, be really kind of irrational numbers, or not irrational, I shouldn't say, but prime numbers. So what we note there, and that should be the case, is that the vector u, or the projection of A on B, is in the same direction as B. So negative I minus j is in the same direction as, whoopsie-daisy, is in the same direction as negative 2i minus 2j, isn't it? So that has the same direction as B, which is what it should do because it's parallel to B. So that's our u, or our component of A parallel to B, and then we can say, well, w, since A is equal to u plus w, w must be equal to A minus u, so that's going to be equal to negative 3, 1 minus negative 1, negative 1. So what's that? Negative 3 plus 1 is negative 2, and 1 plus 1 is 2. Again, numbers that work out really nicely, which definitely won't normally be the case. So that's the vector w there, or the projection or resolute of A perpendicular to B. Now, just to show you how we do it using the formula on your formula sheet. So that would be vector projection of A on B is given as A dot unit vector B times unit vector B. And we'll see why this does have its uses, even though it's not quite as handy to use. So let's just over here go, what is the magnitude of B? Well, 2 squared plus 2 squared, so it's going to be root 8 or 2 root 2. So subbing in here, we're going to get vector A, which is -3, 1 times, or rather dot with, so unit vector B, remember, is vector B divided by its own magnitude. So vector B is -2 over 2 root 2. So it's that times vector B, or unit vector B, which is -2 over 2 root 2. And you can sort of see there that we could then multiply those magnitudes together down the bottom. Otherwise, we'd be saying 1 over 2 root 2, and then the dot product of -3, 1 and -2, 2 is going to be +4, isn't it? And then we've got, so it's all of that times 1 over 2 root 2 -2i minus 2j. So 4 over 2 root 2 is just 2 over root 2. Now we can definitely simplify this, but just putting it in that form, I guess I'm just trying to show you, if this here is unit vector B, in other words, a vector of magnitude 1 in the direction of B, then this other part of the expression here must be the magnitude of vector U. Okay, so that there is the magnitude, because the other part there is just a vector of length 1. So again, that there is the scalar projection of A on B. So this form of working it out lends itself to finding the scalar projection. But if we're actually going to keep calculating U, we'd multiply those two scales together, so we'd get 2 divided by 2, we'd get a root 2 times root 2, which would be a half, and so then we'd be saying -I minus j, and from that we could calculate W again. So not quite as easy perhaps on the working out, because we have these surds, whereas if we do it the other way we don't get any surds, because it's the dot product of a vector with itself. Alright, so there is an example of calculating vector projections.